First, I may need to make a correction, okay? I may. But it's not, hopefully it's not that important. So regarding the definition of Sinc, so one of you just reported to me that most of people in the world define Sinc differently. So I was told by this nice student, a nice guy, that in most other texts, Sinc theta is defined as sine pi theta divided by pi theta. Yeah, so let me go home and make a correction. But either way, this result should still be correct. Just to play safe, just use the standard sign over some this notation. Okay, that's probably less controversial. So I apologize if I make a wrong usage right here. But this should still be correct. So what we're going to do next is to convolve this function, which I do call it Sinc. Okay, because in principle it's the shape of a Sinc function. Yeah, we're going to now. Yeah, now in the last 10 minutes ago, we reached this final expression. We reached this final expression saying that which tells us when we convolve the train of spikes, each modulated with a height of hx bracket n, 中括弧 bracket n. Then the result of convolution can be expressed as a summation of h on the right, of that h function, that h of t shifted to the right and modulated by the same height. Okay, and we sum over everything right here. Okay, we sum over all n. Okay, so now I'd like to invite you to work with me. Then what is the result of summing of this summation? We're going to sum infinitely many copies of the impulse response, each shifted to the right by so much. Okay, yeah. So okay, so let me collect a few chalks. All right, so let's consider the first spike right here. The height is x0. And we are going to put h of t with n equals to 0, right there, right? N is 0, h of t. So we are going to put a copy of h of t right here. And where h of t, which looks like a sinc function, should go to exactly crosses 0 at 1t, and then it goes back and crosses 0 again at 2t, and do this, and smaller, and so on. So that's the first. This is h of t, but with the height multiplied by the height x bracket 0. Okay, so the first thing here is one term. So now I'm going to draw a few curves, and each curve will correspond to one term in this summation. Okay, that's what I'm going to do. So the next curve I'm going to draw is what if n equals to 1? N equals to 1, we have the height of x1. And I'm going to also put a copy of h of t, of the impulse response, which looks like Sinc, but shifted to the right by one sample. Right? So we're going to draw a copy of the Sinc function, but with a slightly higher height, slightly taller, but which is slightly taller than x0. But now another copy of the Sinc function going further down, slide up and down, and this is down right here. And let me draw two more. Okay, so similarly, at time 2, we are going to put each one term correspond to a copy of a Sinc function with different heights. So now the height is x bracket 2, right? So we are going to put a Sinc function right here, which should be about the same height as x0, We promise. So it will probably look like that, something like that. And what else? Probably look like this height. And so on. Okay? And now, similarly, next, you can do it by yourself. And with the height of x bracket 3, we put a copy of the Sinc function, which crosses 0 at exactly the next sample time. And that, and something like that, like that. So that's what we're going to do. Okay, that's what we're going to do. Similarly, just everywhere we have a Sinc function. Everywhere we have a Sinc function, and so on and so forth. And so on and so forth. That's kind of a sketch I'm trying to make. I'm trying to make a sketch to visualize what's going on when we do this summation. And this summation is a result of convolution, of convolving the spikes with our impulse response. Okay? I'll claim to you that convolution here is the result of filtering. So when we design a filter, that filter using any sort of hardware, this is continuous time analog filter. Okay, so conceptually, this is what's going to happen back in the time domain. Okay, back in the time domain. So can you now sort of put everything in your mind, try to see what will happen when we add all the curves together? When we add all the curves, when we superpose all the curve, when we superpose all the curve, the result should be this. The result should be a reconstruction of the original signal. The result should be exactly the same as the original signal after reconstruction. So hopefully this allows you to see, to make sense of it. Okay, to make sense that when we just put all the Sinc functions, add them up together, the result is a reconstruction that should be the same as the original signal. Okay, and we can believe so because in the frequency domain, their spectrum are identical. Because when they are same, when the reconstructed spectrum is the same as the original one, then using inverse Fourier transform, they should be the same. You should expect them to be the same in the time domain. Same in the frequency domain by design, same in the time domain consequently. So that's how reconstruction can happen, okay? As long as our bandwidth is finite to begin with, and we sample at 2 times higher. Sample at a rate that is at least 2 times higher. Right? So I'd like to kind of stop for a while to give you some time to think what's going to contemplate what's going on. 凝视一下, contemplate, okay? To contemplate what's going on right here, same in the frequency domain. Therefore, we expect the result should be the same in the time domain. And by plotting, it sort of makes sense, right? Low pass filter. What is low pass filter? Low pass filter is to make everything smooth. Spikes to begin with, but smooth as a result after low pass filtering. When everything's designed correctly, you expect to get back the original envelope. The original signal in continuous time. Okay, okay, so that's an exercise that hopefully I try to demonstrate to you that you can make a sketch, you can draw a sketch of this convolution, and the result is simply adding all the Sinc functions. And I say that this operation is an interpolation. It's basically you can call it Sinc interpolation. Right? Interpolation 内插啊 interpolation is when I like to use interpolation is when we measure something like in time, in discrete time, and then you try to figure out what happened in between. That's interpolation, right? For example, this is GDP, right? GDP of Taiwan 2023, 2024, 2025. 2000, no, not GDP. Oh no, GDP is not a good. I try to example something that will vary. Give me another example. Interpolation. Come on, let's try to. Can anybody tell me an example of sampling something? And we often need to figure out what happened in between. Well, that's interpolation. 温度. Ah, okay, that's good. So this is temperature, okay? Temperature in Celsius. Okay, so in the morning, 6 o'clock, we have a temperature. And 12 o'clock, we have a temperature, right? And 18, we have a temperature. 24, that's the next day. We have a temperature, right? That's a very good example. Thank you, right? So you take the measurement of the temperature outside every 6 hours, and you ask, what's the temperature of 9 o'clock, at 9 o'clock? What's the temperature at 4 p.m., around right now, okay? Yeah. So that's what we mean to do interpolation, 内插. So as long as the temperature signal is band limited, right, we can perfectly reconstruct the temperature at every moment. That's what it takes a leap of faith to believe this bullshit. As long as the temperature is time limited, not time limited, band limited, then we should be able to make a reasonable interpolation. What's the ideal way of interpolation? That's what we're talking about. As long as the temperature signal is band limited, then the ideal way for interpolation should be using Sinc. Okay, a less ideal but more intuitive way. There are many other options, right? More intuitively, what if we just make linear interpolation? Does it make sense? It makes some sense, right? 6 to 12, yeah, linear interpolation. 12 to 18, linear interpolation. Yeah, it also makes some sense, right? But here we are suggesting that in the context of digital signal processing, using this language, the ideal way, which introduces no spectral distortion, should be Sinc interpolation instead of linear. Okay? Yeah. All right, are things making sense? What does it mean to do interpolation? Okay? To figure out the missing information when we are not making the measurement. Okay? And here, in the context of DSP, is about reconstructing the original signal in continuous time. Okay. Now, thank you for the suggestion. Now, all right. So let me move on in the slides. So now, sort of to summarize using a flow diagram. Okay. So in the textbook, you'll find that this is the Sinc filter that's called ideal reconstruction filter, the Sinc function. Yeah. With ideal response in the frequency domain, Sinc function in the time domain. So what's in this chain of signal processing, we begin with samples on the left. So that's the input right here. When we take the samples, then by specifying the sampling period, we can convert it to impulse train. This is what what's called sequence of impulse train, or what I call the spike train. Okay? We can convert a sequence number into sequence of impulses. And then we apply filter to the sequence of impulses. The result is a reconstructed signal. And the entire thing here, if we just put everything together, is called discrete to continuous time conversion. Okay? A D to C converter consists of first step and second step. First step, second step, and the entire thing here is called an ideal reconstructing system using the Sinc function, right? And that's the notation with D to C box. And you do need to specify the sampling period, okay? Yeah. So far so good? Does it make sense? Just a flow chart. But here are a few more remarks I want to make before we conclude this lecture. The second remark is now we are in a good shape. So now, so far we have introduced C to D as well as D to C, right? So just you can start with any continuous time signal in the world. Define your sampling period and convert it to discrete time, the result being a sequence of number. And you can as well just when you're given a sequence of number, you can convert it back to continuous time. We can perform C to D conversion, we can perform D to C conversion, right? So this entire plot is about just processing our signal in discrete time. The signal any signal in the world is continuous time to begin with. But now with C to D and D to C, we will be able to do some calculation in the discrete time domain. Okay? While when this discrete time system is put with C to D and D to C conversion, then the entire chain is a discrete time processor of continuous time signal. Let me repeat that. Okay? The entire chain of action now, if you think about it, is from the outside, it appears that the input is continuous time, and the output is also continuous time. So both the input and output are in continuous time domain in the world. Okay? While the actual computation can happen in discrete time. And that's much of what we are going to do for the rest of this semester. Okay? For the rest of this semester, we'll just focus on here, assuming that C to D and D to C are both ideal. Assuming that we can, make the conversion. There are certain circuits that you can purchase, that you can use. And we are going to assume that C to D, D to C are both ideal. Okay? Are both ideal. And the rest of the semester, we are going to focus in the middle, because we know that when we put everything together this way, the result is a processor which takes continuous time input and produces continuous time output. And there are many examples, right? Like in music. The input might be your guitar, your electric guitar. The output is from the speaker. Right, but everything in the middle is digital processing. Okay, is possible. Okay, so input is a vibration of a string, 弹吉他嘛, the way you play the guitar. The output is the sound from the speaker. So as a user, you feel like everything is analog, right? You don't need to know DSP in order to play the guitar, right? But the input and output are both in the world, in the continuous time world. Okay? So that's called discrete time processing of continuous time signals. Okay, so the rest of the semester, we are going to follow this framework and study only what's happening in the middle. Okay, So I have a kind of a discussion item right here. What are the advantages? Why don't we just keep playing the old guitar without using digital processing? What's the benefit? What are the advantages of moving the system to discrete time? Yeah? 比较容易 is easier. Any other suggestion? Does it save the energy, save the earth? Probably, I'm not sure about that. Yeah, so there are always different purposes, right? Probably I agree with you that in this entire semester, we are going to see over and over again that discrete time processing is really more simple because you don't need to know semiconductor. Everything's math, right? You hate it or you like it, everything's math right here from now on. You don't need to consider VLSI design issues, and area and energy, nothing. So that's the difference between digital and analog, right? So that's advantage, but the disadvantage might be energy consumption, right? So yeah, be creative. So probably the best system is a combination of analog digital. But this semester we focus in the middle, okay? Discrete time processing of continuous time signals. Yeah. But it's always good to come back to this question and just question yourself, what are the advantages of going digital? Okay? What are the advantages? Yeah. But just let me conclude with this final slide. Okay, so I say additional remarks. I'm not going to put these on the test. Okay, but just so you know that in the textbook, from the textbook, you also see this figure, which begin with a discrete time sequence on the left, but then D to A converter. Okay, a D to A converter with, you do need to also specify the sampling period, and from D to A. We haven't talked about really what it means for a signal to be really digital. You need quantization. You need to introduce rounding. Okay, you need to introduce that. But that's probably going to happen next week. Okay, when you come back. But here, D to A converter, just for your information, the result is a time domain signal. But then there's a different version of reconstruction filter that's called compensated. Okay, compensated reconstruction filter, and there is some analog design issues there. So here, let me just tell you, this filter is not the ideal filter. It's probably that's easier for analog design. Okay, ideal filter is impossible to design, by the way. Ideal filter is not impossible to implement. So kind of said there are design issues, but we are not going to focus on that. But if in case you are interested, you can refer to the textbook. Okay. Yeah. So that being said, that's the end. If you are interested, check the textbook section 4.8.4. Yeah, that's over there. Okay. So with that, let's take like 2 minutes rest, and I will switch to my next lecture. I want to switch to my lecture, but let's take a 2 minutes break.